buzzing, so let's get started. Let's get this show on the road. Welcome to a quiz. I hope everybody brought his mobile phone with him, because otherwise, well, you're not going to win the prize. Anyway, I'm Jago de Vreede. I work for a consultancy company called Open Value. I think everybody has heard of them. But I've seen a lot of projects, and I might have been guilty of premature optimizations. I think everybody has done that before. But Java can help you a lot with optimizing your code, or at least your Java code. It can't really help you with database indexes and that kind of stuff, but let's not move into that space. Let's keep it with Java. So this prize here, it's a chess set made of Lego, so you can actually play it later on. You can win it. It's sponsored by Open Value, my employer. And with that, it's quiz time. If you do not want that Lego set because you're not a child anymore or don't want any Lego, place a dash in front of your name and you won't get it. Then the next person in line will get the prize. So grab out your mobile phone, scan the QR code. The QR code will be on screen at the bottom left. So if you're on the back, I'm sorry. It will be higher up later on. This is a bigger one if you missed it. Everybody got it. So let's introduce Java first. So everybody knows this, right? This is just what we write. Oh, by the way, there are a lot of pop-ups saying you need to sign in. You can ignore that. You just use the username, ignore the cookies, and that kind of stuff. Yes, so this is a normal Java program, but if you compile it, it will be compiled to the Java bytecode. The bytecode will look something like this. It's just not yet machine code. Machine code is done later on, so the Java runtime reads this bytecode. This bytecode can be read from any operating system, and then it's being compiled into native executable code, which looks like this. Luckily, we don't have to look at this a lot, so let's remove from the screen. But if you really want to dive into deeper in this, there's a program called JitWatch, where you can place a Java file, you can run it, and then you can see how the compiler does things and in which state it does what, and you can actually see the machine code being generated and being run at your machine. So that's a nice way of testing this. So Java has a tiered compilation. Well, the first phase is the interpreter mode. This is where all programs start out with. Then you got something called Tier 1 no profiling, limited profiling, then full profiling, and then something called C2. So let's see them in order. So first off, we go from Tier 0, the interpreter mode, into Tier 3. Logically, right? So in Tier 3, there will be counters added and profiling added to your methods. This way, the Java HotSpot compiler knows which part of code take long, needs to be optimized, and are actually called quite a lot. And if they're called quite a lot, after a few thousand times, it will be moved into the second JIT, into C2. But if the compiler is busy, well, optimizing the first bunch of code, then it could be that there is too much overhead with the profiling. And then it can choose to do the counters first. Because if you at least count how many times a method is being used, then you can discard some methods that aren't being used a lot at all. So adding counters gives the HotSpot compiler at least some information, not all information, but some information which can base other results on. And then it goes into the tier 3 and then in fourth tier. But if it has determined that it is a simple method, like, for example, a single line or whatever, it can say, okay, this method is not worth optimizing, this is the best way we can get, and then it can move it into tier 1, and there will be no optimization done whatsoever. So that's good to know. So it's not logically from tier 0 to 4, it's all across the board. So there's a program called the Java Micro Benchmark Harness. And this is the tool that I've used to validate my findings. I can see what the compiler does, and I understand the logic. But it's always nice to validate your findings. So the micro benchmarking harness actually gives a way of validating your results that, well, that they do what they should do. You can use this with a lot of annotations. You can create a class and place a lot of annotations. You can say which kind of benchmark method it should do, like taking average time or throughput or the time unit. If it's a big method, then you might do milliseconds or otherwise nanoseconds. You can say, okay, do at least 3 iterations of warm-up because well, the compiler needs some time to do the warm-up phase, to do the profiling and optimize stuff. So sometimes 3 iterations is not enough. So usually around 5 warm-up iterations, it can give good results. Same thing goes with measurements. Measure once is not good enough. Measure at least 3 times, preferably 5, but it's going to take a long, long time. And you can give it some compiler control. So let's say we don't want to inline some methods. You can actually tell the benchmarking harness to not do that. And then there is a setup method where you can prepare your data. This setting up of data is not well, run in every iteration, or it is run in every iteration, but is not counted as time for that iteration. So only the actual benchmarking method is being used and not the setup method. And then you have a method which you can annotate with benchmark, and you can give it some JVM arguments like the xint parameter. For example, the xint says it should only do inline of interpretation mode, so it should not go to C2. So when you run this, you get some nice results. You can see the score. The score is, in this case, the operations per milliseconds. Well, you can have throughput or averages. You can mix them and match them. So, are you ready? Last time for the QR code. All the questions will be based on OpenJDK 21 and are in fully optimized mode, so in the fully optimized C2 state. That's something you have to keep in mind. Alrighty. Let's start out with the easy one, the var keyword. I think everybody is using var. But if you create a function with var, which one is faster? Is the old-fashioned way of saying int result faster, or is var result faster? Or do they have the same performance? That's always an option. Let's see. We have 33 answers. I don't know how many people are in this call. 34. The code again. Ooh. Here you go. Oh, and by the way, faster answers get more points. So a correct answer is 100 points, and I think the fastest answer is 150 points. So you're not going for the fastest in this way. Oh. So 35 answers. Let's see the results. They have the same performance. And you're doing a lot better than the meetup I did last week. So, so what gives? Well, actually, var is just a synthetic sugar. The compiler will figure out the correct type and will actually place the correct type in bytecode. So if you decompile your bytecode, you will never see the var keyword again because it's just for you as a developer when you're writing code, and when it's compiled, it's just the int. So that's why they have the same performance, because it's the same code. So another one, a string concatenation. We have a final number int, which is an integer. It's 10. We have a that concatenates the number. Then we help the compiler a bit of saying it's a 10. It's a string and in C we have a full string. But how much faster is everything? Is B 10% faster than A and C 20% faster than B? Or is B 50% faster than A and C 20% faster than B? Let's see. $33, I thought we had 35 last time, so might have lost someone, or someone has voted twice in the last round. There you go. They are all the same. So what gives? Well, actually, if you look at the bytecode, it is exactly the same. The compiler will see that this is a final integer, so that final integer will never change. So it can actually inline that in a string. So that string is just that, just a string. And this will be in your bytecode as well. So nothing different in each answer. So next up, inlining. I think everybody knows what inlining is, but for example, we have a function called calc, and that function calls sum. The compiler will eventually see, hey, we don't want to call sum every time. We just can inline the code of sum in the calc function, and then we can use it. But how far can we take this? We have a calc with sum that calls a real sum, and that real sum is then that. Or maybe we can actually create a class, a calculator class, and then call a sum function on that class. Or can we create even a record with a state A and B and then call sum on that state of that record? So where does the inlining stop? Or is everything inlined? There's always an option. Where do you think it stops? Yeah, I don't have any time limits on questions. There's a lot of code on screen. 31, 33, getting there. Alrighty. Actually, everything is inlined. So creating new classes isn't a big performance hit when it's fully optimized. The compiler will see, hey, this class is not used. So there's no need to call a new object. And even with records, it can figure out, hey, that state is only used in that single function. So we can inline that function. So in the end, they will all look the same. I got a question, yeah? So if the class is used anywhere else, yes, the inlining code can be inlined in one place, but won't be inlined in another place. So the calling party, in this case, the call with sum, is the place where it's inlined to. Yes. Good questions, and I like questions if they are. Yeah. Yeah. I think it's, or at least in Java 15 it works. I haven't gone back beyond that, so. But next one. I wish I got paid by the line of code. So sometimes my wishes come true. So I created a do add 10,000. So I have an input that I assign to J. And then I'm going to add 10,000 to that input value. And I do this, of course, by this way. It's only a little under 500 lines of codes, and it goes off screen there. But hey, there are 5,000 plus instructions. Hey, how bad can it be? So that big method, how bad is adding 10,000 this way versus adding 5,000 this way? So adding 5,000 is, well, it's, if adding 10,000 is twice as much, so that's adding 5,000 is twice as fast. Or is it 4 times faster? Or is it more than 2,500 times faster? Or is it 5,000 times faster? Or will they have the same performance? Let's see. Getting there. No, not everything is always the same. At some point, the compiler will give up. So if we look at this, what actually will happen is that the compiler will see, hey, doing the 5,000 thingy, hey, I can actually calculate that you're doing that 2,500 times, and I can collapse that into a plus 5,000. But the add 10,000 is just way too much for the compiler to handle. The compiler will stop optimizing a method when it reaches around 8,000 lines of 8,000 instructions, bytecode instructions. So adding 10,000 will go way over that 8,000 limit. Doing 5,000 addition just works. It gets collapsed. Good question. It's probably 8,996, so probably a magic number in 8. But I think there is a compiler flag that you can actually tune to change this behavior if you really want. But this holds true for every inline option as well. So if you inline specific bytecode to a method, then that bytecode will become part of that method. So at some point, a method contains a lot of inline code, for example, and then it will be just stopped optimizing that piece of code because it's too much for the compiler to handle. But then you are really, really deep in your code. So actually, this is 3,500 times faster than the big method, because the big method needs to do a lot of additions and the small one, just one. All right, a school example. Probably everybody heard, don't do string builder or a string addition in a loop. But how much faster is using a string builder outside of that loop then? Is that 2 times faster? Or is maybe the not recommended way of the plus addition faster? So what do you think? Or do they have the same performance? That's still an option. It's only a little bit more than 2 times faster. So it's not that much faster, but it's noticeable. And actually, if we look at the score, who is Umar? Because we are 1/3 of the way. Who's Umar? Nice. But you are closely followed, so... So what's happening? In bytecode, in that loop, there will be a string builder constructed every single loop time. So that's why it's a little bit slower. Not by much, but it's a little bit slower. So don't do this. Create a string builder outside of your loop. So let's return something. Let's return a string builder then. So which one is faster? The return of the string builder without a temporary variable, or the one with a temporary variable? Yeah, that's the question as well. It's an easy one, right? Right. Right. Well, it's not really fair. It was a trick question. Because you could say, well, actually, you can say that if you would use a big decimal, that they were the same. But we were not using a big decimal, we were using a string builder here. There is a kind of regex pattern in HotSpot that will look for this specific pattern, and this specific pattern only, to do further optimization with strings. And it won't do that with the option 2. It's a little bit faster, it's not by much, but it's 20% faster. Still not much, but hey. So with a big decimal, it will see, hey, that result variable isn't used anywhere, so that can be discarded and then it can return. But not with the string builder. And only with string builder, not string buffer. So that was a trick question. So let's do some simple boxing then. So how much faster is not boxing an integer? So everybody knows that a box integer is an object and not a primitive type. So what is the penalty of using a box? Is it 2 times slower, 5 times, 10 times, 100 times? Or it doesn't really matter? Do you think the compiler is that smart and, well, hey, see, just an integer and just there and it's final? It is not the same, no. It really hurts to create an object. It will actually create an integer object and do stuff with it. And it's around 5 times slower to create a boxed version than the primitive type. So if you do calculations, please do use the primitive type. Another easy one. I think everybody knows this little sonar rule thingy that you need to do the string 0 with the to array instead of the string with the actual data size, that you can actually help the to array to say, hey, we're going to create something with this specific size. But is sonar right here, or doesn't it really matter? In this case, sonar is right. So sometimes static code analysis actually helps. But why? Well, actually, there is an array copy function that's being used under the hood with the toArray. And if you give it a 0-sized array, it can actually do a malloc memory allocation on the entire size of the array. It can calculate how big the array is and do a single memory allocation at once. But if you give it a size, well, it doesn't know if it's a sized object or an object that has some data in it, so it has to go through the entire array and set every element to null. So that hurts, and especially if it's a big array. So null checking then. Okay, this is going to be a more complex example, not by much, but we're going to have a list, and that's a list of strings, and we add a lot of strings in there, which are garbage in this case, but hey, it's a number with a variable size a string, or variable length string. But they are all filled. So we all know that we should do null checking, but we know that the array does not contain any nulls. So how much does this null check hurt us? Does the node null check is less than 2 times faster? Or is the null check more than 2 times faster? Or more than 5 times faster? Or are they the same? Let's see, 34. They are the same. It's always the same. So what's actually happening under the hood is that the compiler will see, hey, this method, you never give it a null string, so it actually will remove that null check for you. It will actually not work. So you might think, okay, but what if I give it a null after this optimization has been done? Well, actually, then a normal way of machine code actually happens, then a segmentation fault will occur. Because you will get a null pointer at some place it didn't accept a null pointer. So what it then does is, well, it will de-optimize your code, run in interpreted mode, execute your code again, and see what happens then. Well, then there's a null check, and then it will actually fall through. If you somehow messed up and did a s.length, for example, in the null check before the null check or whatever, then it will actually have a null pointer, and then it will do a segmentation fault again, but then it will actually be a null pointer, and that would be returned. So the compiler can de-optimize based on unexpected behavior. So in the end, in C2, those pieces of code are exactly the same. So don't worry about null checks being well, hard for the compiler or hard for Java. So let's do some math then. Let's get back to Java 8. Java 8 is a long time ago. Java 9, there were a lot of improvements, but what happens to math? Is Java 8 faster in math, or is Java 9 2 times faster than in math, or 4 times faster? Or are they the same? I see that Anthony is gaining. Who is Anthony? Anthony G. All right. Everybody, or at least most of you, got this one right. Java 9 is actually 4 times faster in math operations than Java 8. So if you do a lot of math-heavy operations and you're still on Java 8, this is another way of getting more bang for your buck. So actually in Java 9, they changed the math library. So we would use actually more CPU instructions instead of doing the software versions of, for example, square root. There's a CPU instruction for square root. It's on all modern CPUs, and well, Java now can use that specific CPU instruction instead of doing it by itself. So that's a lot faster. 4 times faster. Okay, let's do some for loops then. Let's get back to the basics. Which one is faster, the for loop with the for I or the old school while loop? Just the same piece of code, but it's for against the while loop, or are they all the same? Well, all these two. I think you're catching up on me. Actually, they are the same. And do you know why they are the same? Because they are the same. It's just a fancy way of saying a while loop. So if you write a for loop, it will actually get compiled into bytecode as a while loop. If it gets decompiled, it will see, hey, this is that fancy pattern that you had, so that must be a for loop. So if you actually wrote a while loop, compiled it, and then somebody decompiled it, and then they will see, hey, a for loop. So, all right, another one. The while iterator versus the enhanced for loop. What do you think? And what do you think? That was slow. So is the iterator faster, the for each? Or are they the same? You're getting up on me. Well, yet again, the enhanced for loop is just a fancy way of saying a iterator. You actually need to implement the iterator if you want to do some enhanced for loops. It is call it an enhanced for loop because it's just a synthetic sugar on top of the while iterator. So they are exactly the same, so they perform the same. So let's take these all together. There are more ways than one to do for loops. We have the iterator, we have our old-fashioned for loop, or the while loop, but we also have a classic lambda that we can give the list for each, or we have a method reference. Which one is faster, fully optimized? And I keep clicking the wrong button. 33, 34. In fully optimized C2, they are all the same. It's just a loop over a set of data, and the C2 compiler will see that, and it will do exactly the same to each and every one. Funny to see that nobody thinks a classic lambda is faster. There are multiple answers to this question. There are some pattern recognitions, and there are some simple recognitions, and well, it will never compare results of one thing. Well, actually, well, yeah, and then magic. A lot of unicorns died in the process. No. But let's do this question again, but not in fully optimized mode, but in interpreter mode. So the mode that you probably will run in the first phases of your application, and rank those answers. So they're not all the same, or maybe they are because it didn't fit on the slide, but it is an answer in the app. So is the method reference the fastest, then classic lambda, iterator, for loop, iterator, method reference, and then classic lambda, or the iterator, for loop, classic lambda, and then method reference? What do you think? How do they rank? $31. Does anyone need to see the code again? 33. And no, they're not the same. There's actually a good explanation for this as well. So let's dive into that. Well, this is the answer. The method reference is the fastest. Then comes the classic lambda. Then comes the iterator, and then comes the for loop. But why? So if we look at the iterator versus a for loop, then we'll see that the iterator is a little bit faster compared to the for loop, because the for loop needs to do 2 concurrent modification checks instead of 1 in the iterator. So the concurrent modification check is heavy, or at least in this example. So that's why the iterator is a little bit faster than the for loop. But you can actually increase the for loop a little bit, or the for loop, by not using the list.size inside of the for loop, because then the list.size needs to be calculated every single iteration. But if you extract it to a, let's say, final variable on top of your for loop, then that actually gives you, well, 1,000 milliseconds, in this case, a performance benefit. So that's a nice, easy trick. But then comes the classic lambda versus method reference. Well, a method reference is I think it's an invoke dynamic or invoke static call directly. So that's just a function call. But with the classic lambda, well, you actually write a new runnable object and you create a new object. And well, the compiler didn't have any time to say, hey, this new runnable doesn't do anything, we don't need it. So it actually creates it for you. It doesn't do anything, it just hurts you. That's why the classic lambda is a little bit slower than a method reference. And that's why. So we have value of. We have an integer.value of, and we have a I that is a random number between 1 and max int. But we also have a new integer. Well, Sonar again says we should use value of. But is value of faster or not? What do you think? Well, they're not the same. New is a little bit faster than value of. But then again, why? Well, if you do integer.value of, it will actually need to check a integer cache. Because if you give it an integer between minus 128 and 128, it will come from an integer cache. So it needs to do some checking first, and then, if it's not in the cache, do a new integer. It's again also a method call that you need to do. So instead of all that plumbing, calling method, checking cache, and that kind of stuff, you do directly new integer, which is probably going to do anyway. That's why the new integer is a little bit faster than the value of. Alrighty. Before we give out the prize, I will give you this quote. It's from Sir Tony Hoare from December 47, so it's quite an old quote. We should not forget about small efficiency, let's say 97% of the time. Premature optimization is the root of all evil. Then Donald Knuth made it a popular quote by adding, yet we should not pass the opportunities in that critical 3%. Well, I like to combine it and say, write clean code first and optimize a specific piece of code if you identified significant issue with it. So just write normal code like any normal people, because you write code for your fellow developers, and don't go berserk and think you are smarter than the C2 compiler, because you're probably not. And with that, we have a winner, and that's called D-Man. Who's D-Man? Doesn't want Lego? It's Mr. Duncan over there. Doesn't want any Lego. But Anthony, you came second. So get over here and claim your prize. And of course, Mr. Duncan, congratulations. And also congratulations. And with that, the animation, crap. Anyway, thanks for your participation, and please rate the talk in the Jago app, and enjoy the rest of the conference.